Okay, let's dive right into this. 86 billion. That's roughly the number of neurons firing away inside your human brain right at this very moment. It's this staggering, beautiful biological mystery. But, when you hear the term artificial neural networks in the news, it's so easy to picture a digital replica of this exact biological wonder. But as we're going to see, artificial networks are actually vastly different. They aren't biological magic, they're built on pure, elegant mathematics. So, welcome to this explainer on neural networks. It is ridiculously easy to get lost in all the heavy sci-fi jargon when we talk about AI. So let's just strip all of that away. We're going to look straight under the hood at the mathematical engine of modern artificial intelligence together, moving all the way from the tiniest microcomponents up to the massive architectures that are literally changing our world right now.
Here's our roadmap for today. We'll start with number 1, how they're not quite a human brain. Number 2, the math behind the learning. 3, specialized networks for complex data. And finally, number 4, inside the AI black box. All right, section 1, not quite a human brain, moving from sci-fi to mathematics.
Just look at the stark contrast here. A real brain neuron has dendrites receiving signals, a cell body processing them, and synapses where these chemical messengers bridge the gap to the next cell. It's a messy, highly complex chemical reality, right? With temporal dynamics and structural changes happening all the time. On the flip side, artificial neural networks are really just inspired by this biology. Kind of in the same way an airplane is inspired by a bird. The artificial principles are fundamentally different. They rely on numerical inputs, adjustable weights, and strict mathematical operations. So what exactly is our artificial birdwing? Well, it's called the perceptron. Invented way back in 1958 by Frank Rosenblatt, this is the absolute fundamental building block. It's the smallest microcomponent we're going to be working with today. A single perceptron simply takes several numerical inputs, does some basic math, and produces an output. But to understand how it actually makes decisions, we need to take a look at its internal mechanisms. And that brings us to weights. You can think of weights as adjustable parameters, or literally just mathematical knobs. When a perceptron receives a numerical input, it multiplies it by a weight, and this determines how important that specific input is to the final decision. When we say an AI model is learning, what's actually happening behind the scenes is that it is systematically turning these mathematical knobs, adjusting these weights to make better predictions, whether that's predicting the weather or, recognizing your face to lock your phone. Next up, we add a bias term. Imagine bias as a neuron's default enthusiasm. It's basically an adjustable threshold that shifts the activation point. So a high bias means the neuron is incredibly enthusiastic and will fire easily, even with super weak inputs. A negative bias? Well, that means it's stubborn and needs massive positive input to trigger a response. Together, weights and biases form the adjustable internal settings of our whole model. But we need one more ingredient to make this whole thing work, and that's the activation function. This is a mathematical formula, maybe a curved line or a sharp threshold, that the final number is passed through. This right here is the secret sauce. Why? Because it introduces nonlinearity. Real-world data is complex and messy. It doesn't just fit on perfectly straight lines. Activation functions are what allow networks to bend and map to that complex, curved real-world data. This point is captured perfectly in this quote from our source material. Without them, the entire network would be equivalent to a single linear transformation. It's truly staggering to think about. Without activation functions, you could stack billions of neurons together, and they would just mathematically collapse into a single, flat, simple line. They wouldn't be able to learn anything complex at all. Okay, moving on to section 2, the math behind the learning, how a network actually learns. All right, here is the full training pipeline. Think of this as a repeatable mental map of the algorithm in action. First step, we've got initialization, where we assign random starting values to all those weights. Then comes the forward pass. You watch the data flow through the network to make a prediction. Next, we compute loss, which is purposefully measuring exactly how wrong that prediction was. After that, backpropagation kicks in, working completely backward through the network to figure out which specific weights caused the error. Then we update parameters, adjusting those mathematical knobs to fix the mistake. And finally, iterate. We just repeat this entire cycle over and over again for millions of examples. Now, step 5 is where the true magic happens, but it raises a massive question. Imagine you're dropped onto a mountainous landscape with millions of dimensions. You're completely blindfolded, and you need to find the absolute lowest valley, which represents the lowest possible error or loss. Seriously, how do you find the lowest valley while blindfolded?
Well, the answer is gradient descent. You feel the ground right around your feet, figure out which direction slopes downward the most steeply, and you take a step, hopefully without tripping over a parameter. Then you repeat. Gradient descent is powered by a calculus chain rule technique called backpropagation, which computes exactly how much each individual parameter needs to wiggle to get you further down that hill. It is absolutely the workhorse optimization algorithm of machine learning.
Section 3. Specialized networks for complex data, scaling up for sight and language. Because we're feeding in complex reality, different data types demand entirely different designs. On the left here, we have convolutional neural networks, or CNNs. They deal with spatial data, like images. Their job is seeing. On the right, we've got recurrent neural networks and transformers. They deal with sequential data, like text or time series. Their job is remembering. Processing space requires a vastly different mathematical approach than processing time.
Let's actually zoom in on CNNs for a sec. If you connected every single pixel of a high-res image to a network, you would need billions of weights. It's computationally impossible. CNNs innovate by using local receptive fields, meaning they focus only on small 3x3 pixel areas at a time. They also use parameter sharing, where they slide the exact same mathematical filter across the entire image to detect vertical edges and then another one for horizontal edges. And this automatically builds this beautiful hierarchical feature learning. The early layers discover simple edges, middle layers combine those into textures, and the deep layers assemble it all into a fully recognized object, like, say, a cat. Now, this architecture didn't just happen overnight. Think of it like an escalating construction project over decades. We started with a perceptron back in 1958. Fast forward to 1997, and long short-term memory networks, or LSTMs, were created to help networks remember long sequences of data. In 2012, AlexNet, which is a deep CNN, sparked the modern deep learning revolution by completely crushing image recognition competitions. And then in 2017, a tectonic shift happened in the world of sequential data. In 2017, the transformer architecture dropped, bringing with it the attention revolution. Previously, networks had to read text sequentially, word by word, which meant they'd often forget the beginning of a long sentence by the time they reached the end. Transformers introduced this self-attention mechanism, and this allowed the model to process all the words in a sentence simultaneously, computing mathematically how much every single word should attend to or relate to every other word, completely regardless of distance. This parallel processing is exactly what powers the massive language models like ChatGPT or Claude that we interact with today. Which leads us to Section 4, Inside the AI Black Box, the Frontiers of Interpretability. We are absolutely living in the era of the black box now, because these modern models consist of billions, sometimes trillions of parameters, all interacting nonlinearly. They've become vastly, almost eerily opaque. Even the brilliant engineers who build these networks cannot easily peer inside and reverse engineer exactly why the model made a specific decision. It's an incredibly profound mystery. It's this dense web of mathematical weights that completely defies easy human interpretation. And look, this isn't just some fun academic puzzle for computer scientists. It's a critical hurdle for actually deploying AI in the real world. Just think about the massive stakes here. Doctors simply cannot trust an AI's medical diagnosis if they don't understand its reasoning. Engineers struggle to debug failures when the system gets something disastrously wrong. Regulators are actively demanding a right to explanation for automated decisions. And on top of all that, these black boxes are incredibly vulnerable to adversarial examples, where a tiny invisible mathematical change to an image can completely fool the entire network. Which really just leaves us with this final, kind of provocative thought to chew on. As these neural networks get larger and better at manipulating statistical patterns perfectly, predicting the next word flawlessly, or recognizing an image perfectly, does the system actually understand meaning? In cognitive science, this is known as the symbol grounding problem. The AI has no subjective experience, right? It is just executing gradient descent on billions of weights. So when an AI says something profound, is it actually understanding or merely simulating understanding? I'll leave you to ponder that one. Thank you so much for joining this explainer, and I really hope you leave with a much clearer picture of the beautiful math driving the AI revolution today.